So everybody's got a copy of the lesson, I hope. Ooh, that's really loud. That would have been a little loud. If we can turn in our lesson to, how about example 7? Example 7, which asks, what average force is needed to stop a bullet of mass 20 grams and speed 250 meters per second as it penetrates wood to a distance of 12 centimeters? We're there now? Example 7? Okay, forget about whatever test you have later on today. Focus here. Okay. Terry, what's this question asking me to find, number 7?
The average force.
Okay, this is, okay. I noticed they gave me a speed and a distance, and there's an average force. You know what I think this is probably wanting me to do? I think they want me to realize that work equals the change in kinetic energy plus the change in potential energy. Now, how did I figure that out? Well, Terry, the fact that they said speed, that's a bit of a hint. I think they want some kind of a scalar approach. I might be able to do this using kinematics, V final, V initial, or find A. Well, let's see what we got here. I don't see a change in height. I think this bullet's traveling straight, so let's do that. What's changing anything? And I think the final, because it says to stop, is going to be 0 minus a half m v initial squared. And on the left-hand side of my equation, I have work. What are my different definitions for work? I've already used the work energy theorem, which is the work is the change in energy, but I think I can also say this. And the reason I said work is force times distance is, Jaron, what were they asking me to find here? Average force. In fact, I'm going to get this. Force times distance equals negative a half m v initial squared. I think the force is going to be negative 0.5 m v initial squared, and just divide that by the distance. And what we're really saying here, the reason this is a conservation of energy question, is we're saying, look, the bullet lost kinetic energy. That must mean that that block of wood did work on the bullet, because that block of wood changed how much energy the bullet has. Where'd the energy go? I think most of it went into deforming the wood, and then probably some of it went into heat. I don't know if you've ever fired a gun into a tree, but you can sometimes see that the hole the bullet leaves behind is charred. There's a fair bit of heat going on there. Let's start crunching numbers. What do we get? Force equals, oh boy, late student. So I think I'm going to get, now the negative in my final answer, I think I'm just going to ignore, but what it's telling me is the force is being applied in the opposite direction of motion. Oh, we've got somebody else coming in now too. Another interruption, but I think we're good now. A half. The negative is telling me that we're in the opposite direction of the force, of the force is in the opposite direction of the bullet. Let's try that again. Negative, a half. Mass of the bullet, it says, is 20 grams, which is 0.02 kilograms, right? 250 squared divided by 0.12. What do you get? What is the average force to stop a bullet? 0.5 times 0.02 times 250 squared divided by 0.12. 5,208 newtons. Anybody else? Yep. Fair bit. Well, yeah, it's probably stopping a bullet's fairly tough. That's why even bulletproof vests, when people get hit by them, they hurt and break ribs and things. Okay. 5,210 newtons. And I dropped the negative in this case because I don't think it's a direction. I think it's a, well, anyways, I asked for average force. I didn't give you any directions in the question, so I don't think you could say to the left or to the right. Example 8 says a 3,000 Newton car at rest. Hey, that's probably important. Oh, and you'll notice, Ben, they didn't give me the mass of the car. They gave me the weight of the car because it doesn't say 3,000 kilograms. What does it say? 3,000 what? That's the mg. I guess they've done that already. That's nice of them. At the top of an incline 3 meters high and 30 meters long is released and rolls down the hill. What is its speed at the bottom of the incline if the average friction force is 200 newtons? I'm going to draw a little picture. Here's our car, here's our hill. Okay? Well, I think this looks like the job for conservation of energy. How do I know? I'm seeing a change in height and a change in speed. That usually means energy is a good approach. Am I going to include heat this time? Well, I do notice they're talking about friction force. So I think what I'm going to say is this. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final plus heat. Are any of these zero? Ah, I'm coming to the, hitting the ground. Sure. Starting at rest. So I think I'm going to have this. A half, no, not a half, Mr. Duke's potential energy. Good gosh. mgh initial equals a half mv final squared plus, and here's my problem. Heat. What the heck is heat? Can't be heat because newtons is force. And heat's got to be measured in joules. Josh said 200 newtons. I mean, he's on the right track. I think I'm going to be using that for something. I think heat is the work done by friction. That's heat. Terry, work is what? No, Jaron, work is what times what? It's force times the distance? I think if I take this distance, because that's where friction is acting, in that direction along that ramp, I think the heat is going to be the friction force times the distance of the ramp. I think I can say mgh initial equals a half mv final squared plus the force of friction times the ramp distance. Do the masses cancel? No. What are we trying to find? I think V final. Okay. Well, I think I'd minus force of friction times the distance on the ramp over. I think I'll have this. mgh initial minus force of friction times d. And then I guess I would divide by 0.5 m. I think that equals Vf squared. Oh, how would I get rid of a squared? Okay, let's square root that because I'm running out of room. If that's okay, Chelsea. Is that right? I think that's it. Pardon me? Is that all right? Right? I'd minus and then I'd divide, I think. Let's plug and chug. Let's see. I don't know the mass. Oh, but I know mg. mg is 3,000. So I just need the height times 3 minus force of friction, 200, times which distance? Not the height, the length of the ramp, 30, all divided by 0.5. Ooh, I need the mass. Well, if the car has a weight of 3,000 newtons, how can I figure out the mass? You know what? I'm even going to write right here, 3,000 over 9.8. I think my calculator can handle that. Let's see. I'll do the square root at the very end. It's going to be 3,000 times 3 minus 200 times 30. That's the top part. Oh, conveniently 3,000. Divided by bracket 0.5 times 3,000. Let's put that in brackets. Times 3,000 over 9.8. Close the bracket. Square root. I get 4.43 meters per second. Question? I don't think this one's complicated enough, Dorothy. I don't think I'd try doing it all in one step. The nerd within me kind of wants to try. You'll notice I did the whole top line, hit enter. I divided it carefully by the bottom line and then square rooted. If you're wanting an easier way to get that, Dorothy, you might even go like this. 0.5, the bottom, times 3,000 divided by 9.8. Then you might go, here's the top. 3,000 times 3 minus 200 times 30. Close off the top, divided by the answer for the bottom, and then square root that. It gets you there. Anyhow, technical comment on ramps. Normal force does no work. Why? Well, work is force times distance in the same direction as motion. Normal force is always 90 degrees to the motion. And this goes back to the equation that I said the other day when it was, you could also think of work as force times distance cosine theta. If you're 90 degrees, cosine of 90 is 0, for those of you who have done Math 12. So if the ramp is frictionless, unlike this one, if the ramp is frictionless, the energy of the system is conserved. The same argument applies to tension in a pendulum cord. So rope swing is a great example of conservation of energy. Tarzan has a mass of 85 kilograms, and he's going to run straight forward at 6 meters per second. He runs, he grabs onto a vine, and lets his momentum carry him up, swing him up until he stops. Write a work energy equation, and how high can he swing? How do I know to use energy here? Well, I'm visualizing Tarzan running this way, but then swinging this way. It's a curvy path. Oh, let's use scalars, energy. Are any of these 0? Pardon me? Now, Dorothy, you asked a great question. Dorothy, this is important. Ask your question. This is. Here's the beautiful thing about conservation of energy. We can make 0 any height we want to. That's convenient. Let's put the height of 0 right at Tarzan's center of mass so that we can just pretend he's starting out on the ground. That's the beauty of conservation of energy. In other words, in answer to your question, let's do that. And what we're really finding is how high his center of mass swings, which means whether we measure from the top of his head to the top of his head or the bottom of his toes to the bottom of the toes, the answers will be right anyways. Dorothy says, with brilliance in her mind, is kinetic energy final 0? Let's see, if I'm saying how high can you swing, then at the very top of your swing for a split second, how fast will you be traveling? Yeah. In fact, what we're really talking about is, if I get my little pendulum set up, Mr. Dewick, Tarzan's running along, running, and he hits the rope and he does that, right? And the nice thing is, it doesn't matter whether I hold this here and do the math, or hold this up here and do the math. What I'm really going to be finding is I'll treat this as 0, and that difference will be the same no matter what. Why? It's a scalar. So Dorothy has told us she's pretty sure the equation is going to be a half mv initial squared equals mgh final. Dorothy would be right. Dorothy, in her continued state of brilliance, might even notice one more thing. Turns out I didn't need to tell you how much Tarzan weighed. Now, I've done the rant about, oh, you don't get on a scale before you go into a roller coaster. The limiting factor here would be the strength of the vine. So Tarzan probably could swing. Tantor the elephant, maybe not so much. In theory, would arrive at the same height with the same amount of, same velocity. Okay, the vine would snap, right? This is, we're in our magical physics world where stuff all works nice. How high can he swing? So there's my equation. B says, hey, how high can he swing? Final height equals VI squared over 2G. Is that right? I would divide by G. And then to make this look pretty, instead of having a half, how about I put a 2 in the bottom? Because that looks like a nice, pretty equation. In fact, I'm actually sort of seeing the VI squared equals, or VF squared equals VI squared plus 2AD in disguise again, because I got my 2A on the bottom, yeah, and I got, anyways, 6 squared all over 2 times 9.8, not negative because it's a scalar. 1.84? Meters per second, Mr. Duke? It's a height. How about meters? And the best place to analyze or to use conservation of energy, where it works the best, roller coasters. Roller coasters. Because roller coasters have curvy hills. And the nice thing is, Jaron, because energy is a scalar, all it cares about is how high you started and how high you ended. As a matter of fact, if this hill went like this, still wouldn't make a difference, because whatever energy I lost going up, I'd gain going back down, and so mathematically it would be the same as if I started from that height. Here's our roller coaster. If this ramp is frictionless, and a good roller coaster is close, well greased, well lubed. Write a work energy equation and find the speed of the 1,000 kilogram roller coaster at the bottom of the ramp. And then B says, if the speed of the ramp is 12 meters per second, write a work energy equation and find the energy lost to friction. I like this question. I like this question. And I like it for several reasons, not just because of my usual, I like this question, I like this question, I like this, but my other it's a roller coaster! Here's the physics. Let's do A. Taylor, is there a change in height? Is there a change in speed? Is it a curvy path? This looks like a job for conservation of energy. I'm trying to give you, so that by the end of the year when you have all these different methods, what do I do when? If you give me a change in height, a change in speed, and yuckiness, energy is my fallback. And in part A it says frictionless, so Megan, no heat. Okay. Any of these? 0. Yeah. And again, Jaron, I highly doubt in real life that right here is actually 0 high. Most roller coasters that I see are a couple meters off the ground because you step up onto a little platform. Doesn't matter. We'll just let that be 0 because that works mathematically for us. Nice. A half mv initial squared plus mgh initial equals a half mv final squared. Hey, Jaron, have you been on a roller coaster before? Did they step on a scale, make you weigh before? You know why? Any of you remember, the Playland doesn't have it anymore, but they had for years, they had the Wild Mouse roller coaster. Remember that one? Because that's a scary one because you swear you're going over the track. That's scary for two reasons. First of all, because none of the corners are banked, you really feel the G-forces. And the other reason it's scary, I don't know if you ever noticed, but in the roller coasters, they had little sandbags for ballast. Okay, I like rides, but when you're having to add weight, okay, now the masses aren't canceled. Oh, okay. Anyways, yeah, real world. They did. You know what else I'm going to do, by the way, Jaron? I'm going to go times by 2, times by 2, times by 2. Because it'll cancel. Now, I think this is a great trick, Sydney, but a lot of kids kind of get sloppy with this. The halves and the 2's cancel, but there's still going to be a 2 in front of the GH. I get VI squared plus 2GH equals VF squared. It's really VI squared. VF squared equals VI squared plus 2AD, but we're using this notation. What do they want us to find? In part A, Ty, what do they want us to find?
Part A?
Yeah.
Find the speed of the roller coaster.
In this equation, what are they asking me to find then? VF squared?
Yeah.
They want me to find the speed squared? What are they asking me? You with me now? What are they asking me to find, my friend?
Yeah.
How do I get rid of a squared? Let's do that. So I'm going to get this. V final is going to be the square root of, yeah, thank John for bailing you out. V initial square, 2 from the diagram, plus 2 times 9.8 times 10. So 2 squared times 2 times 9.8 times 10, get an answer, square root. 2 squared times, Mr. Dewey, plus 2 times 9.8 times 10. Square root of 200. Should be about 14.1. Yeah. Meters per second. Now that's if there's no friction. Part B says, all right, suppose you're on the roller coaster and you got a little radar gun and you measure the speed of the roller coaster as it comes by and you notice it's only going at 12. Where'd the other energy go? Got to go somewhere. Law of conservation of energy says it's got to go somewhere. Hey, both my dippy birds are working now. They somehow revived themselves over the weekend. There you go. Okay. B. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final plus heat and sound and, well, we'll just call it all heat. I think once again, John, I can cross that out. They're asking me to find the energy loss to friction. I think that's really the work done by heat. I think they want me to get this by itself. How would I get that by itself? You're right. Say it louder. I've told you I like this question. I like this question. Every year, for some reason, kids divide by kinetic energy final, and I don't know why. Which makes it way yuckier, by the way. Anyways, it's minus. So I'm going to get this. The heat is the initial kinetic, the initial potential, minus the final kinetic. However much energy you started out with, minus whatever energy was left in the roller coaster, okay, whatever's left after that must have gone into heat. It's going to be a half mv initial squared plus mgh H initial minus a half mv final squared. But Bob, do the masses cancel this time? Why not? There's a mass in everything. Oh, no, there's not a mass in everything. There's no mass in heat. Okay. That's common mistake number 2. Kids are, oh, Mr. Duick, he did his little scale rant. I don't need a well, no, in our real world, there is some friction. But as long as I can keep the friction pretty low, then I don't need to step onto a scale before getting onto a roller coaster. Let's plug in the numbers and crunch. How many joules of heat were generated? 0.5 times, what was the mass, Mr. What was the mass? 1,000. There it is. 2 squared plus 1,000 times 9.8 times 10. Come on, decimal. Minus 0.5 times 1,000 times V final, what do they say? 12 squared. Okay. Heat. How much? You get 26,200? No? Am I wrong? A half mv squared is 2, plus 1,000 times 9.8 times 10. The height was 10, wasn't it? Minus...
0.5 times 100 instead of 1,000.
There we go. Thank you. Second function, insert an extra 0. You get 28,000?
Yes.
Woo! Okay, that's better. And that's the 2 or 3 sig figs, and heat is measured in joules. So the homework that I gave last day that I said technically you could try, now is officially you can try. It was 1, 2, 3, 4, skip 5. Well, skip 5, skip 8. Okay? I'm going to give you a few minutes, but then I'm going to try and fit a second lesson in today. Sorry, sucks to be you.